If we measure the reaction rate as the change in concentration of reactants or products per unit time, we understand that as reactants get consumed, products are formed. The amount of reactants goes down, the amount of products actually increases as time is going by. So if we think about a hypothetical reaction where we have just reactant A turning into product B, A is disappearing as B is appearing. Reactants are used, products are made. If I think about how to express that rate is equal to the change, and that's the delta sign, the change in the disappearance of reactant A over a set time interval, delta T is change in time, which would be equal to the rate of appearance of the concentration of B over the change in time. Reactants get used, that's the negative sign. The concentration of reactant decreases per unit time interval as the amount of product B is being formed, that's the positive sign. So as reactants get used at the same rate, products are formed. If I think about the concentration of B at time 2 versus the concentration of B at time 1, that's what the change is representing. So rate really is an expression of the change in concentration per unit time. And I'm going to put brackets to show concentration most often is measured in molarity units. The change in concentration per unit time. And that's the delta T part. So suppose instead of generic letters A going to B, we look at a familiar equation where nitrogen combines with hydrogen to form a molecule called ammonia. And we see a 1:3:2 stoichiometric ratio. We would notice, and just kind of thinking about this in terms of an XY axis, let's suppose, let me get my camera shifted a little. Let's suppose on an XY axis, we think about what's happening. We have a certain amount of the reactants, hydrogen and nitrogen. Time is going by and the concentration of hydrogen goes down. Reactants are consumed. Nitrogen also goes down. And notice what I'm trying to draw is that the rate at which hydrogen disappears is 3 times that of the rate at which nitrogen disappears. And at time 0, we wouldn't have any product, but eventually product would form, and it would be right between the nitrogen and hydrogen. So the concentration of hydrogen going down at 3 times the rate of the concentration of nitrogen, and twice that for the production of ammonia. Just a visual of what's happening in terms of kinetics. The reaction progresses and the concentration of hydrogen goes down. Reactants get used. As the reaction progresses, the concentration of nitrogen goes down 1/3 as fast. Want over given ratio, 1/3. All as the reaction progresses, the ammonia molecules goes up, and it's going to lie right between the two with its coefficient of 2. 2 moles worth of ammonia are formed. And I've shown that by drawing those 3 lines onto a set of axes. Reactants get used as products get made. If we want to calculate rates, we have many different ways to do that. The 2 that are provided in our text are known as average rates. And average rates are taken over long intervals of time. For example, if I have an initial concentration of 1 molar and it dropped to 0.9 molar in a course of 10 seconds, this is a reactant decreasing in concentration, we would solve that by noting the change in concentration of our reactant over the change in time. It's an average rate. The second way we could calculate a rate is known as an instantaneous rate. I didn't spell it. Instantaneous rate. There's not enough N's. An instantaneous rate. That's determined by finding the slope of a line tangent at the curve at any given point, because the rate isn't changing over time, it's happening at an instant. It's known as a derivative to the calculus buffs out there. Let me represent these in terms of a graph. An average slope method says, thinking about as time going by, we're measuring the concentration of a reactant. We'll call it reactant A. As time goes by, we notice that reactants get used, so their concentration decreases. If I take an average slope method, I find a time interval. When I think about how much the concentration changes per unit time, I'm finding an average rate. It's the rate of a reaction. I'll write that RxN, the rate of a reaction over a particular time interval. That example might show the change in concentration would be initial of 1 molar, final of 0.9 molar, and I'll reverse that to show I know that reactants get used, so it will come out negative, over a course of 10 seconds. How much the concentration changed by a certain time frame, an average slope method. A second way to calculate that, and let me represent that on a graph, is called an instantaneous slope. Let's consider the same set of XY axes, concentration versus time, and we'll just call it reactant A. I'd like to know how fast the reaction is occurring at an instant in time, not over an interval of 10 seconds, but right here at this time. How fast is it occurring? We do that by taking the tangent to that curve at that particular instant in time. So the rate of a reaction at a certain time is called an instantaneous slope method. An average slope, we need 2 time intervals. How much the concentration occurs over a time interval. An instantaneous slope, how fast is that reaction going right now? And that's considered to be an instantaneous slope by finding the tangent. Stoichiometry and reaction rates. In general, if we look at an equation with generic letters, where the little letters are representing the coefficients and the capital letters are representing the reactants going to products, we have reactant A with its coefficient of A, reacting with B to form C and D. How would we represent the rate of that equation? Well, this rate is given by, again, negative, because we are looking at